Hey, good afternoon, everyone. My name is Valerio Carollo. I'm Senior Project Leader in the numerical modeling team at TWI, a research and development company in the United Kingdom. And today I'm going to present an overview of the result of a European project that I'm coordinating, that is a Clean Sky 2 project that is developed in collaboration with the University of Cambridge, RTM Breda in Italy, and GKN Aerospace in Sweden. The title of the presentation is an experimental and numerical framework for the assessment of fatigue performance of damage in Incone 718. This is the outline of the presentation. I will briefly give an introduction of the state of the art of the problem and the challenges. Then I will provide a project overview with the project activities and the work performed so far, and finally some conclusions. So this European project, the main objective of the European project is to predict the fatigue life of damaged Incone 718. And the industrial application for this is because Incone 718 is used in aircraft turbine blades, which are affected by small damage during their service life, caused by small objects that impact at high velocity, or during handling and repair operation with like tool dropping on a turbine blade. In order to take into account those small damages at the design stage, a linear elastic fracture mechanic approach are used, which do not take into account of the compressive residual stresses under the damage. So they are very conservative design. And this is proven even in literature, where there are studies and it's known that the residual stresses improve the fatigue life. In fact, here we can see on top right the fatigue crack propagation rate of a scratch when there are residual stresses and when the residual stress have been released, stress released. And we can see that the crack progression rate when there are residual stresses is way lower, and this results in an increase in fatigue life of over 2 times. So the Clean Sky project I'm working on want to develop an experimental and numerical framework for the prediction of the fatigue life, taking into account this the residual stresses, the damage and the residual stresses. The approach we use for the project is divided in 2 main activities: an experimental campaign and a modeling activity. In the experimental campaign, we are going to characterize the material, the Incone 718, in the elastoplastic property, fracture property, and fatigue property. Then we're going to develop the damage with dynamic indentation for a split optics on pressure bar. And the damage that we are going to develop the damage in fatigue specimens, and this damage is going to be characterized from microscopy images, and also the residual stresses beneath the damage is going to be characterized. And then the specimens are going to be tested to retrieve the low cycle and high cycle fatigue property at room temperature 550 degrees, where 550 degrees is the operative temperature of the turbine blade. Then we use all these experimental data that we produce to calibrate and validate numerical models for the prediction of the residual stress during the impact, and also for the prediction of the fatigue life, taking into account the damage and the residual stresses. And once we have the validated model, the final step is to perform an uncertainty quantification to understand the effect of the damage, the different feature of the damage on the fatigue life. So the first step of the project was to plan our damages and our indentation. So we identify as key parameter for the damage the depth of the damage and the radius of the tip, and the ranges that were given by GKN, the topic manager of the project, were for the radius between 40 micron and 1000 micron, and for the depth between 50 micron and 300 micron. You can see on the right an example of the indenter that we would use we are using for the dynamic indentations. So considering this range of damages, then we built test matrix that considers 5 different damage configurations that takes into account 3 different depths and 3 different radius. And then the damage is performed through Hopkinson bar, where on the bottom you can see a representation of how the Hopkinson bar works. There's a striker bar who strikes against the input bar. At the end of the input bar, there will be the specimen, and then on the opposite side, at the beginning of the output bar, there will be the indenter. So the specimen strikes against the indenter that push away the output bar that then is stopped by a momentum trap. So we start the setup. We start develop this dynamic indentation procedure, taking care of the setup with many preliminary specimens. We first wanted to understand if the smaller damage was detectable, since it was almost the same order of magnitude of the manufacturing lines, and we verified that it was possible. Then one of the biggest problems we had was due to wave reverberation of the bar. So we were having multiple indentations, and they will not create a neat damage, and we will have reproducibility issues. So we explore different ways of solving this, and at the end, fortunately, the solution was to have a bigger input bar and a smaller output bar. So the momentum that was transferred from the input to the output bar was enough to push the output bar far away. And then another issue was related with the integrity of the indenter, because we wanted to the indenter to be clear when there was some fracture of damage, in order to have, again, high repeatability of our damages. We initially used some hard magnetic steel that was having some plastic deformation and small damages, and then we passed to tungsten carbide, which is brittle, and when it fractures, it fractures. Then we pass to the design of the specimen. We designed the fatty specimen with a rectangular cross section in order to have a flat surface where to perform the damage. We make sure that he had the same this geometry didn't affect the fatigue life, testing both type of geometry, the classical round one and the one with the rectangular cross section. And then a problem that we were having was the distortion of the specimen during dynamic indentation, which is a problem found in literature, where people usually or perform the indentation statically, or they flip the specimen and perform another one to put it back. And we did a sensitivity study on the thickness of the specimen. Also, to help the design, we calculate the KT along the damage through finite element analysis, where take into account a small misalignment of the indentation to see if this was affecting massively the KT or if the specimen will start nucleating a crack still from the middle of the damage. And with this, we verified that the tolerances that we had in place were enough to guarantee a good repeatability of the damage. Last slide. Then we're implementing, we're validating a numerical model for the prediction of the residual stress, modeling all the setup of the Hopkinson bar with the input bar, specimen, indenter, output bar, and using elastoplastic material property with strain dependency through a Johnson-Cook model. So in conclusion, we are working for the development of this experimental numerical procedure for the prediction of fatigue life in Incone 719 affected by damages, and the final result should be the uncertainty quantification. Thank you so much. I would welcome any questions now.